What do you feel like when you look at the sky above you? Have you ever felt the need of science and mathematics you study at school while understanding the patterns you observe in sky? Definitely not, because there is no need of science and mathematics to differentiate between the phases of moon, trace some constellations or observe the motion of a few noticeable planets. In every culture, astronomy was born before mathematics because there is no need of mathematics to look at sky. In India, those beginnings were not adequately documented, but that does not mean that there was no significant progress. India's first astronomical objects that were found in the Andamans belonged to the Paleolithic era and were as old as 12,000 years. They are calendar sticks recording lunar phases across several months. Ring stones found at Mohenjo-daro exhibit rows of small drilled holes which have been interpreted as calendrical devices keeping track of sunrise at different times of the year. The perfect east-west alignment of streets in the same city has been attributed to the sighting of the star cluster Pleiades. While the above examples remain speculative, it is well understood that ancient people everywhere felt a need to relate to the universe. In the Vedic period, the four Vedas, which formed the earliest body of Indian scripture, began as an oral tradition and then were written in Vedic Sanskrit after passing down through different generations. These four Vedas are Rig Veda, Yajur Veda, Samaveda, and Atharva Veda. The oldest Veda, Rig Veda, made the first attempt to reconcile the lunar and solar years. It also recorded a solar eclipse, although in a metaphorical sense. It has recently been proposed that its mention of 3339 gods was a reference to Saros, an 18-year cycle of eclipses. All these references clearly point to a very early tradition of astronomical observation in Indian subcontinent. A few centuries later, the Yajurveda almost accurately considered a solar year of 365.24 days and a lunar year of 354 days. It divided the year into 6 ritus or seasons of about 2 months each. It also gave the first list of 27 nakshatras or lunar mansions that are the constellations along the path of the moon in the Earth's stellar background. Calendrical astronomy grew more sophisticated towards the end of the Vedic period due to the need to keep time for the proper conduct of rituals. The Vedanga Jyotish was the representative text of this period and thus we call it the Vedanga Jyotish period. The Vedanga Jyotish discusses about solstices or Ayanant and equinoxes or Vishava. It also uses an intercalary month or Adhik Masa to catch up the lunar calendar with the solar calendar. The text considers the length of a sidereal day as 23 hours 56 minutes 4.6 seconds, while the exact length of a day is 23 hours 56 minutes 4.091 seconds. This tiny difference is the indication of the precision reached in that early age. Until this period, the month was only divided into 2 fortnights or pakshas, that are Shukla Paksha and Krishna Paksha. Vara or weekdays and Rashis or zodiac were not mentioned in Vedang astrology. The early historic period was marked by astronomical computations based on the risings and settings of planets. their revolutions, etc. Jaina astronomy also developed in the same period. This is also the period when huge scales of time were conceived of, such as a day of Brahma or Kalpa of 4.32 billion years, which curiously comes close to the age of Earth, that is about 4.5 billion years. It is noteworthy that Babylonian and Greek influences started from this period. For example, the 12 signs of Rashis or zodiac were recorded just after the end of this period. Another example is the introduction of the 7-day week system of Varas that took place in the next period, that is, the Siddhantic era. Beginning in the 5th century CE, it is the Siddhantic era, what has been called as the golden age of Indian mathematics and astronomy. Siddhanta is a Sanskrit word meaning principle or conclusion, but here it refers to the collection of conclusions or a treatise. The celebrated mathematician astronomer Aryabhatta I was born in 476 CE and worked near what is today Patna. He ushered in this era with his Aryabhatiya, dealing concisely but systematically with developments in mathematics and astronomy. It discussed units of time and features of a celestial sphere, describing Earth as a rotating sphere hanging in the space. Aryabhatta gave the correct explanations for both lunar and solar eclipses. He stated that the diameter of Earth is 1050 yojanas, defining 1 yojana as 8,000 average human heights, or about 13.6 km. This estimate of 1050 yojanas comes close to the actual dimension, though 12% too large. One of the Aryabhatta's contemporary, Varahamihira, composed a collection of 5 astronomical texts prevalent during his time, which is known as Panchasiddhantika. One of the 5 texts, Surya Siddhanta, was revised later and became a fundamental text of Indian astronomy, while 2 others expounded the principles of Greek astronomy. Varahamihira extensively discussed the revolutions of planets, eclipses, and the zodiac, often with an astrological background. Bhaskara I, who was born in 600 CE, is the earliest known exponent of Aryabhatta and has provided a very useful elucidation of Aryabhatta's astronomy and improved calculation methods. A few years later, Brahmagupta, who was born in 598 CE and lived near Mount Abu, mistakenly rejected Aryabhatta's view of the Earth as a rotating sphere. But nevertheless, he contributed much to the calculations related to the mean and true longitudes of planets, as well as problems of lunar and solar eclipses. Brahmagupta also authored a manual of astronomical calculations, which remained popular for centuries, as testified by Al-Biruni, the Persian savant who came to India in the 11th century as a part of Mahmud of Ghazni's entourage. Biruni was deeply interested in Indian astronomical techniques, and hence he wrote about them at length and translated texts by Varahamihira and Brahmagupta into Arabic or Persian. The Indian astronomers could not have achieved so much without a strong tradition of observation. The 22nd chapter of the Brahmaspata Siddhanta, written by Brahmagupta, deals with a variety of astronomical instruments. Bhaskara II, better known as Bhaskaracharya, brought important innovations to both astronomical and mathematical techniques, discussing in particular the mean and true position of planets, the triple problem of time, direction and place, the rising and settings and conjunctions of the planets, eccentric and epicyclic theories for their motions of planets, and a large number of astronomical instruments. Overall, Bhaskaracharya greatly improved upon the formulas and methods adopted by early Indian astronomers. During those centuries, astronomy's interface with the general public was mostly through calendars and panchangas, and the prediction of eclipses, which had great religious and social significance. Indeed, an astronomer's fame was guaranteed if he could accurately predict the occurrence, nature, and duration of eclipses, and numerous inscriptions record a king's reward to such an astronomer. For instance, this is an inscription recording King Ratnadeva's donation of a village to astronomer Padmanabha for predicting a total lunar eclipse. Over 350 such inscriptions from 440 to 1859 CE have been traced out. Another interface was architecture, and many temples show clear astronomical alignments with events such as the sunrise at solstices and equinoxes, such as the Sringeri temple, whose mandapa is dedicated to the 12 rashis or signs of zodiac, and some of the pillars are aligned to the sunrise on the two solstices. The widespread belief that there was virtually no progress in Indian astronomy and mathematics after Bhaskara II is based on a general ignorance of the intense developments that took place in the southern state of Kerala. The so-called Kerala School of Astronomy and Mathematics flourished there from 14th to 17th century, when networks of knowledge transmission in North India were severely disrupted in the wake of repeated invasions. Parameshwara, an author of some 30 works, was one of the foremost astronomers of this school and the founder of the Drik system, which improved computations of eclipses and the positions of the planets and proved to be very popular. He was followed by Nilakant Somayaji, who in his landmark Tantra Sangraha carried out a major revision of the older Indian planetary model for the inferior planets Mercury and Venus and described them along with Mars, Jupiter and Saturn as moving in eccentric orbits around the Sun. This achievement of the Kerala School of Astronomy is truly remarkable in the light of the fact that Nilakantha preceded Copernicus, the propounder of the heliocentric theory in Europe. About the same time, a complex interface with Islamic astronomy took place, which among other benefits brought instruments such as astrolabe to India. The famous and massive Yantra Mantra or Jantar Mantar observatories built in the early 18th century by Maharaja of Jaipur, Savai Jai Singh, represents a convergence between Indian, Arabic and European astronomy. The Indian astronomy interacted not only with the Islamic and European astronomies but also with the Chinese astronomy, which, in complex interplays, invariably enriched both the players.